Cool. So I'm Mahimna. I'm a PhD student at Cornell University in Cornell Tech. And today I'll be talking about Poisson Regression. And this is joint work with Phi, Mariana, and Karn, who are all at Google. So the general area of this work is within privacy-preserving machine learning, and more specifically, secure computation. So here the goal is for two or more servers to learn something useful about their private data without revealing the data itself. So prior work in this direction, for example, has looked at things like linear regression, where you want to learn a linear model, or logistic regression, when you want to learn a binary predictor variable, or even more complicated things like neural networks. In this work, we'll look at another model, Poisson regression, which has widespread applications in the natural and social sciences, but has not yet been explored in the secure computation literature. So Poisson model is used to model count or rate-based data. So in this model, the distribution of the response variable y, given the set of features x, is a Poisson distribution where the log of the parameter lambda is linear in x. So in other words, you can have some weights vector theta such that the expectation of y given x is e to the power of the inner product between theta and x. And to compare between different time intervals or to model rate-based data in general, you also have another variable t, which models the exposure. So Poisson models are quite useful in a lot of applications. So in medicine, for example, they're used to predict mortality rates given things like demographics or habits like smoking or alcohol use. They've been used in politics to understand voter turnout based on different kinds of news media exposure. They've been used in finance to predict credit default rates and determine who loans are given to. In online advertising, they can also be used to measure ad click-through rates and purchases. And in all these cases, there's a lot of sensitive private data at stake, like medical data or demographic information. So it's really important to be able to learn these Poisson models securely. So before I describe our secure algorithm, I'll briefly describe what the plaintext version of Poisson regression does. So there's n training data points, where the ith point contains the response yi, the exposure time ti, and the vector x of m predictor variables. So the goal is to learn a set of regression weights such that each yi is approximately ti times e to the power of theta times xi. So the standard way to learn any kind of functionality like this is through gradient descent, which will update weights at each iteration according to the gradient. So the gradient will be computed by minimizing the loss function negative L, where L is the log likelihood function. And now to compute the gradient, you can think of it as x transpose times the difference between the actual response y and the predicted response t times e to the power of theta x. And in each iteration, the weights are updated as a linear function of the previous weights and the gradient computation. So here we have two parameters, alpha, which is the learning rate, which says how quickly we want to update the weights, and beta, which is the regularization parameter, which makes sure that we don't overfit to the training data. So now in the secure setting, let's say we have n data points of user data. So our work is in the two-server model, where these data points will be secret shared between two servers, who will then take part in a secure 2PC protocol in the semi-honest setting to jointly compute the weights of this regression model. So let's take a look at what kind of computations are required in this secure computation. So we have a few matrix multiplications, like multiplying x times theta. We have some element-wise multiplications, which are just n multiplications. And we have some exponentiations to exponentiate e to the power of theta x. And this is particularly challenging in MPC because it's highly nonlinear, and this will be one of the contributions of our work. So the full contributions of our work can be stated as we give the first efficient two-party protocol for Poisson regression, which takes 4 rounds in total, and 3 if there's no exposure variable. And the same protocol can also be used for secure inference after the training is complete. We provide practical performance on real-world data sets through our protocol. So there's 2 main building blocks for our work. The first is a highly efficient 1-round protocol for secure fixed-point exponentiation. And the second, so this is orders of magnitude better in both the offline and online phase than existing techniques such as using polynomial approximation. And the second is improved preprocessing in what we'll call correlated Beaver triples. And this takes advantage of the structure of operations required for Poisson regression. And it turns out using this, you can have 1,000 times faster offline phase and 10x smaller communication. So let me briefly discuss some preliminaries in that all of the data is given as fixed point numbers, which can be thought of as numbers with h integer bits and f fractional bits. And these numbers are represented as integers by multiplying them by 2 to the f inside an L-bit ring z2 to the L. So where L is greater than h plus f plus some slack delta, which makes sure that the failure probability is small of the whole protocol. So positive real numbers are represented in the lower half of the ring, and negative real numbers are represented in the upper half of the ring by multiplying by 2 to the f. And under bar v will denote the canonical real associated with this fixed point ring element. So when I say v in this ring is secret shared, what that means is the two parties have shares v0 and v1, such that v equals v0 plus v1 mod 2 to the L. I'll also briefly mention an operation ring change, which we use heavily for converting shares between one ring zn and another ring zk. So we only really require this for small positive elements and only when we want to move up in ring size, so when k is greater than n. And in this case, it turns out that this operation can be done completely non-interactively, which helps with the complexity of our protocol. So I'll start with the first building block, which is our one-round protocol for exponentiation. So the functionality is roughly as follows. You have two parties with shares of the exponent, and they want to end up with shares of e to the power of that exponent. So a quick note is that it's actually sufficient just to exponentiate with base 2, because for base e, you can just non-reactively multiply by log base 2 of e. So the protocol intuition for this exponentiation is as follows. So we separate out the integer and fractional parts of the computation and exponentiate them separately and later combine. And this actually results in multiplicative shares of the final computation up to truncation or rounding errors. And this is quite nice because all of this can be done completely locally and without any interaction. So the only interaction that we need is to convert back from multiplicative shares of the result to additive shares of the result, which only requires one round of communication and a single message exchange between the parties. So in more detail, if you have, let's say, a share zi, you can split it into an integer part zi int and fractional part zi frac, and you can exponentiate them separately. So you can see that the integer parts can actually be thought of as sharings over a smaller integer ring, which is z2 to the L minus f. And the fractional parts can just be thought of as real numbers. So to exponentiate the integer part, we can leverage Fermat's little theorem to do this non-interactively. So in particular, first we can ring change from this integer ring to zq minus 1, where q is some arbitrarily chosen L-bit prime. And now you can exponentiate locally mod q to get multiplicative shares in fq. So basically, if you had some value w equals w0 plus w1 over the ring zq minus 1, then doing 2 to the w plus q minus 1 mod q is just 2 to the q because of Fermat's little theorem. For the fractional exponentiation, we use another clever trick, which is to understand that these fractional parts are just small positive reals. So if you exponentiate them and try to project them onto the ring, then the shares won't wrap around the ring because they're small. So this actually means that you can just exponentiate them locally and even in real numbers to get a multiplicative sharing up to the truncation of the final result. And this also ends up giving us a smaller error than using other techniques like polynomial approximation. You can, after you've done the integer and fractional exponentiations, you can multiply locally to get shares of up to truncation of the complete exponentiation result. And these will be multiplicative shares. All of the computation so far has been completely local. So the only communication step we need is to convert from these multiplicative shares to additive shares. And for that, we can use existing techniques which require only one field element transfer per party in a single message round. And finally, we can convert the sharing back from the field zq to z to the L using our ring change operation. So the protocol I described actually only works for positive exponents. You can handle negative exponents by assuming a lower bound and then adding it to the exponent at the start and dividing it out later. And this bound naturally arises within Poisson regression. A couple caveats about this protocol is that it cannot detect computation failures without greatly sacrificing efficiency. But the failure probability can be made arbitrarily small by just increasing the size of the ring that you're working in. It's also an open question if the efficiency carries over to the malicious setting, because you need to exponentiate things in real numbers, let's say, to get the smaller error. So it's unclear if this carries over to the malicious setting. As a few concrete benchmarks, our preprocessing requires just 2 field elements for preprocessing and 1 element for communication per party. We have a smaller error than polynomial approximation, which is about 7x smaller when you have 20 fractional bits, and the gap widens with more bits. For some concrete benchmarks, in the offline plus online setting in the LAN network, we can do something like 236,000 operations per second in a 63-bit ring, and 15,000 operations per second in a 127-bit ring. And this is significantly faster than existing works for exponentiation, which do orders of magnitude smaller even in just the online phase. The second building block that we have is preprocessing using correlated Beaver triples. So as a refresher, multiplication or Beaver triples are used for preprocessing to multiply 2 shared inputs, and they can be generalized to matrix triples as well. So the triple is shared matrices A, B, and C, such that A times B equals C. And now to multiply U and V, you publicly first reconstruct U minus A and V minus B. And now the shares of the multiplication is just linear in the triple, and so can be computed locally. Now let's take a look at the gradient computation again, and notice that in each iteration, one of the multiplicands in the computation is the same. For example, you need to compute multiplications x times theta 1, x times theta 2, and so on, with the same x and different weights in each of the iteration. So the idea is we can reuse the preprocessing for the common multiplicand. And this leads to our correlated Beaver triples. So if you have many shared multiplications, then we can preprocess these correlated triples by just having the same matrix for the common multiplicand. The upshot of this is that U minus A only needs to be reconstructed once. And this leads to significant gains in both computation and communication when U is much larger than all of the Vj. And this is exactly the case that we have in the Poisson regression protocol. In terms of end-to-end performance results, we tested the accuracy of the weights that we got in the secure protocol with the ones we got in the Plaintext protocol. And we can see that for the variety of learning rates, the learning is exactly the same. And in fact, we calculated the root mean square error and found that it's very small, roughly 10 to the negative 4 or 10 to the negative 3, depending upon the different data sets between the plaintext and the secure weights. As a final point, we also have some end-to-end benchmarks for specifically with 3.1 gigahertz and 32 gigs of RAM per party in a single-threaded code in a LAN network. As a concrete example, if you have 10,000 samples and each of them have 100 features, and if you run the whole Poisson regression protocol for 100 iterations, this is the results that we get. The baseline comparison is with standard triples and exponentiation through the scale Mamba protocol. So we have 5 minutes of total offline time, which is 25,000 times faster than the baseline. We have 9 minutes of total online time, which is 50% faster than the baseline. And we have 1.5 gigs of communication, which is 200 times smaller than the baseline. And this is for all of the 100 iterations of the regression protocol. And that sort of concludes my talk. Here's a link to the paper, as well as an email address if you want to reach out. I'll take any questions.